Hi everybody. So in this lecture, I'd like to talk to you about quantum confinement of metals versus semiconductors. Now, in a little bit of a recap, this builds off some of the other lectures we've done. We've already introduced the ideas of quantum dots and nanowires, and we've already discussed quantum confinement in kind of a general way when we talked about how if you're within a few deBroglie wavelengths, if your particle size was within a few deBroglie wavelengths, then you started to exhibit properties of quantum confinement. And in that lecture, I also mentioned that semiconductors were really the choice for creating a quantum dot because semiconducting materials can achieve quantum confinement at a larger size than a metal, and that makes the quantum dots a little bit easier to make, of course, if they're larger. So I'm going to elaborate on these points and delve a little bit more into the science behind them in this lecture. So first of all, remember that for metals, a lot of their properties are dependent upon this free electron gas or free electron C of the conduction electrons. And if you start to shrink the particle size down, then that means that how far those free electrons can move gets to be quite restricted just because of the size of the particle. Now, if you start to restrict the movement of those free electrons, that's naturally going to change a lot of the properties of the metal. And that's because the free electrons are responsible for so many of the wonderful properties that we rely on for bulk metals, like their lustrous color and shine, their conductivity, a lot of their thermal properties, things like that. And so if you start to mess with how much the free electrons can move, then that really is going to change a lot of the properties. But what kind of typifies the idea of quantum confinement for a metal is this, what happens is that as you shrink the particle size down, the metal will go from being a good conductor to being an insulator if you shrink the particle size down enough, okay? So the reason for that is, as we've discussed, your Fermi energy is the highest energy level occupied for something at 0 Kelvin. And as you increase the temperature, it goes from kind of like a step function looking energy distribution to a rounded off. But the Fermi energy is still a good measure of the highest energy level for those electrons. Now, in a metal, of course, what happens is you have your conduction band and your valence band. In a metal, those are the same thing. Okay, so the conduction band is the valence band for a metal. As you shrink down the size of a metal particle, you're also reducing the total number of free electrons. Remember that most metal atoms contribute 1, 2, or 3, generally 1 free electron to the free electron C, or free electron gas. And so you'll have about 1 free electron roughly for every atom that you have. If you only have a few atoms, your energy level structure goes from looking like a continuous band to looking like discrete energy levels, okay? So it goes to start looking like discrete energy levels. If that happens, then what happens is something like this picture here on the right, which is a figure from your text. You see here that this is a nanoparticle. It covers all the energy states from 0 up to the Fermi energy are covered. That's the highest occupied energy state. But if you just have a few free electrons, then the spacing in between neighboring energy levels is, visible, measurable, right? Some delta E, finite value of delta E that you can see. In other words, it doesn't look continuous anymore. Now, if your highest occupied level then is slightly below the Fermi energy, okay, because of the reduced number of energy states, then eventually what will happen is that thermal energy, this KT thermal energy, will not be enough energy to kick it up into the conduction band anymore. And that's just because, you just don't have that many electrons. So the way to measure this is this equation right here. This is a nice rule of thumb equation, where this delta E, the spacing in between the energy levels, is, as we said, roughly the Fermi energy divided by the number of conduction electrons. But this gets a little more specific than that. 4/3 the Fermi energy divided by the number of conduction electrons N. And if this spacing is related to KT in this way, greater than KT here, then it won't have enough energy to jump up, as is shown here in this little diagram. Okay, and it'll sit there and it'll be an insulator, just naturally be an insulator. And you'll have to give it energy in order to excite it into the conduction band. In other words, it stops acting like a metal and starts acting like an insulator. And that's called the metal to insulator transition. Now let's do a little calculation based on this, and this is also discussed in your book. So for most reasonable temperatures, only electrons within KT of the Fermi level can become conduction electrons. So let's look at silver, for example. Silver has a Fermi energy of about 5.5 eV, which if you put it in SI units is about 8.8 times 10 to the minus 19 joules. And it also contributes 1 conduction electron per atom. And so if you're plugging into that equation that we showed on the previous slide, that delta E, 4 times the Fermi energy divided by 3N, right? Then here's this 4/3 times the Fermi energy, about 8.78 times 10 to the minus 19 joules, divided by KT here. Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. And then room temperature, let's just even kick it up to about 311 Kelvin, okay? So that it's kind of hot, right? And if you do that, then you end up with N of about 272 electrons, okay? So 272 electrons means 272 silver atoms, because each silver atom contributes 1 free electron. So you can use the density of silver then to estimate the size of the particle that you would see then that would exhibit this quantum confinement. So the density of silver is 10.5 grams per cubic centimeter. Using Avogadro's number and the molecular or atomic weight of silver, 10.5 grams per centimeters cubed times Avogadro's number, 6.022 times 10 to the 23rd atoms per mole, divided by the atomic weight, 107.9 grams per mole. That tells you the number of atoms per cubic centimeter that we have for silver, which is 5.86 times 10 to the 22 atoms per centimeters cubed. Okay? Now, if you take that and you invert that number, 5.86 times 10 to the 22 atoms per centimeters cubed, then you would have the volume per atom, okay? So to find the volume of the nanoparticle, you would take the number of atoms and divide it by the volume per atom, so that's 272 divided by 5.86 times 10 to the 22, and you end up with a volume for your nanoparticle of 4.6 times 10 to the minus 21 cubic centimeters. Now, if that volume is then assumed to be a sphere, then you set that equal to the volume of the sphere, which is 4/3 pi r cubed, and you can solve for the radius of your nanoparticle. And that would give you a radius of 1 nanometer. So, you know, radius of 1 nanometer, diameter of 2 nanometers, that's about how big that you would have for quantum confinement in silver. Now let's talk about semiconductors, okay? Semiconductors we can't approach in quite the same way. And that's because of the band gap in the semiconductor. So in a semiconductor, of course, the electrons aren't already, the valence electrons aren't already conduction electrons. In order to promote something to being a conduction electron, you have to excite it out of the valence band and into the conduction band. And the amount of energy that's in between the valence and conduction band is known as the band gap. So when you excite that electron into the conduction band, what that does is it leaves behind a vacancy, which we call a hole in the valence band. So the absence of the electron actually has a net positive charge, right? So the holes themselves, the vacancies, act as positive charge carriers, and you can even calculate what the effective mass of these positive charge carriers are. Now, a little bit of jargon, electron-hole pairs are known as excitons. Okay, so that's a term that you'll see a lot of for electron-hole pair. Now, these vacancies or holes, which have a positive charge, and the conduction electrons are attracted to one another because opposite charges attract. Now, lots of times, the electron, because it's attracted to the vacancy, will want to recombine and then fall back into that vacancy. And it'll emit a photon via energy conservation when it falls from the excited state back into the valence band. And then the energy of that photon will equal the band gap energy. And this is what happens in LEDs, light emitting diodes, and things like that. But sometimes they don't recombine, or they don't recombine right away, and they're still attracted to one another. If that's the case, then you can model that attraction like an orbit, like you would, for example, in the Bohr model of the hydrogen atom, where you have a proton and an electron attracted to one another, and then the electron orbits, okay? So the Bohr model is used as a guide. If you do that, then you can estimate the radius of the exciton orbit, okay? And so in this equation, we call A sub EX, or AX, the exciton radius. And then that's going to be roughly equal to, or estimated as, the Bohr radius, which is mostly symbolized by A naught, A sub 0, times the dielectric constant divided by the effective mass of the exciton. So remember that the dielectric constant kappa is equal to the permittivity of the material, which is epsilon, divided by the permittivity of free space, which is epsilon naught. Epsilon naught, of course, is 8.854 times 10 to the minus 12 in SI units. But the permittivity of the material that you're looking at will vary from material to material. It's a property of the material. Okay? As a reminder, the Bohr radius is 0.053 nanometers. Okay? So here's the dielectric constant, effective mass, and exciton radius for some common semiconducting materials. So, for example, silicon here is on top. It's got a dielectric constant, which is epsilon divided by epsilon naught, or kappa, of 12. The effective mass of the exciton depends upon whether what direction it's moving, whether it's moving longitudinally or transversely. But you can see it's expressed as a fraction of an electron mass. So, 34% of the mass of an electron for longitudinal motion. And then that gives an exciton radius of 2 to 5 nanometers. Now you can see that right away this is already 2 to 5 times larger than the radius of that metal nanoparticle that we talked about before. If you go down the list for the other semiconducting materials listed here, for example, it ranges from 3 to 18 nanometers for the other particles. So you can see that using this model, you've got a larger size for the particle still exhibiting quantum confinement. So this exciton radius is a nice ballpark figure for estimating when something is going to exhibit the traits of quantum confinement. You can go smaller than that exciton radius and it'll be very, very confined, or you can go slightly larger than the exciton radius and it'll still be confined, okay? But not as much, all right? So, but roughly around that amount, around the exciton radius, is quantum confinement for semiconductors. Now, as we discussed in a previous lecture on quantum dots and their properties, in both metals and semiconductors, restricting the motion of the charge carriers causes that quantum confinement, okay? And for quantum dots made out of semiconductors specifically, if you change the size of your particle, okay, and you get a changing size, that also changes the band gap of the material. So when you change the size of the particle, you're approaching that exciton radius for the quantum material, and it starts to exhibit particles more like an atom, right, than it would a bulk material. And that's the quantum confinement threshold there. When that happens, you're also going to see a changing band gap for the material, as we discussed previously. Smaller particles have larger band gaps. So after this lecture, I hope you can understand a little bit better why that is, okay, why that is. So that sums it up. That wraps up what I wanted to say in this lecture. Let me know if you have any questions, and I'll see you in class.